So far we've seen a bunch of tests where the structure of the sequence, so A sub n, or the rule for the sequence is like very specific. It's geometric or it's a p-series or whatever. So, but what happens when we have um, a series, a rule for a series, or A sub n, that is not as straightforward? So what we're going to do is look at some more complicated series like um, the sum of n over 2 to the n. This is like close to a geometric series, but it's not. So what we need to do is compare to a function what we're going to try and do is compare to a series that is easier to take the test of, or to figure out, to use a test to see if it converges or diverges. Okay, so we have the direct comparison test is one way that we can one shortcut for us to see if our series converges or diverges. We have if we know our sequence A sub n is between another sequence and 0, then we can use two rules to help us figure out convergence or divergence. So the first is, if the series B sub n converges because it's larger than A sub n, then A sub n will also converge. So if I look at my picture over here, the larger is B sub n. The smaller is A sub n. So I know if that the area under B sub n, the larger series converges, then the smaller series will also converge. All right? So let's look at the next condition or situation that can happen. If A sub n, the smaller function series converges, if A sub n, the smaller series diverges, then we know that the larger series will also diverge. So we can look at it over here. If the smaller series diverges, then we know anything larger than it will also diverge. Okay? So what we're trying to do is choose a friendlier series so that we can use another test like the p-series test or the geometric series test to determine convergence. So if the series converges or diverges. Okay. Then in general, a good series to use is the harmonic series 1 over n, because it's like really, really close to converging, but it doesn't, it diverges. So it's like right on that line between converging and diverging. So I don't know, it's a good one to use. Okay, so we're going to determine the convergence or divergence of each series. So I have the sum from n equals 1 to infinity of 1 over 2 plus 3 to the end. And I'm like, oh, that's a little more complicated, but I think I can compare to 1 over 3 to the n. And I know that 1 over 3 to the n compared to 1 over 2 plus 3 to the n, the denominator will be larger in the second fraction. So that means that the value will actually be smaller when I divide. So the 1 over 3 is B sub n. It's larger than our original. So what we know is that since B sub n is the one that we're going to be evaluating later, if B sub n converges, then A sub n will converge. So that's what we're hoping for. We'll see what happens. Okay. So here's what we do. We're going to test to see the sum as n equals 1 to infinity of B sub n. So the series that's easier to take to figure out if it diverges or converges. Okay. And then we're going to compare it to our original. This is like a geometric series. I like that. 1 times 1 over 3 to the n. I see that my r value is 1/3, okay, which is less than 1. So the series from the sum from 1 to infinity of 1 over 3 to the n converges by geometric series test. Therefore, our original series that we know is smaller, it's smaller than b sub n, will also converge. This is 1 over 2 plus 3 to the n, okay, converges by direct comparison test. All right, moving on. So we do need those two pieces of information, like how does the comparing series, how do we know the comparing series diverges or converges, and then how does that relate to the series that we are actually evaluating? All right, up next, the sum from n equals 1 to infinity of 1 over the square root of n minus 2. Like, let's try and compare to 1 over the square root of n, because that would be a p-series, and I know I can figure out convergence and divergence of a p-series. So let's just see. 1 over the square root of n, how does that compare to 1 over the square root of n minus 2? So if I plug in the term 10, 1 over the square root of 10 versus 1 over the square root of 10 minus 2, I see that when I subtract the 2, the denominator is larger, so it's going to be, sorry, the denominator is smaller, so the fraction itself is going to be larger. So this one is b sub n and a sub n. So since I am actually taking the evaluating convergence or testing for convergence and divergence of a sub n, this is what my graph looks like. It's the smaller function, okay? So what we know is that if the smaller function diverges, then the top one will also diverge. So anything above it will diverge. We can't say anything, if a sub n converges, I don't know if b sub n converges or not, because it's larger than the function that the series that I have now, okay? So I am going to go ahead and look for the convergence of 1 over the square root of n. So I'm going to do the sum as n equals 1 to infinity of 1 over n to the 1/2 power. This is a p series. So p is equal to 1/2, which is less than or equal to 1, but greater than 0. So the series, the sum from n equals 1 to infinity of 1 over the square root of n, it diverges. I'll just put diverge by p series. And because it's the smaller series, then I know the larger series will also diverge. Therefore, the sum of n equals 1 to infinity of 1 over the square root of n minus 2 also diverges by direct comparison test. Okay, last example for today. Okay, here's the deal with this one. I have the sum as n equals 1 to infinity of 1 over 4 times the cube root of n plus n minus 1, excuse me. So I am going to, I don't know. It seems like I'm going to test some things out. Okay, so if you're not sure what's happening in a series, just expand it. See what happens, okay? So I'm going to plug in 1 for n, and I get 1 over 4 times 1 minus 1 plus 1 over 4 times the cube root of 2 minus 1 plus 1 over 4 times the cube root of 3 minus 1 plus, and this goes on for a while, okay? And I am literally going to plug this into my calculator because I want to kind of see what it looks like. So I'm just going to graph it. Notice it kind of looks like this. So I decided that I want to try and compare to 1 over n. Okay. So I am going to graph this because it seems easier to figure out when these cross, because I'm going to plug in 1 over 1. I'll go and expand 1 over 2 plus 1 over 3 plus 1 over 4 plus dot, dot, dot. And what I'm noticing when I graph this is that the second function, 1 over n, is larger until a certain point where they cross. So let's go ahead and figure out their intersection. First curve, second curve, guess. So we know that the two curves intersect at 6.44, comma 0.155. So what this tells me is that the function 1 over n is less than the function 4 times the cube root of n minus 1 for n's that are greater than or equal to 7. We're just using whole number integers here, okay? Positive integers. So because we're plugging in term numbers. So it's okay to exclude a finite number of terms. Well, finite number of terms, because those finite number of terms doesn't affect whether the series converges or not. So what we're really concerned about is what happens in the tail. Is the tail decreasing fast enough for us to converge? Converges or not. Okay. All right. So what I know is that since 1 over n is a sub n, because it's a smaller curve, has the smaller outputs. Okay, that's a sub n, b sub n. We're hoping that a sub n will diverge. We hope that it diverges, because then it'll tell me that the larger curve, the larger output curve, b sub n, will also diverge. And I think we chose the right series, because as the sum of n equals 1 to infinity of 1 over n, we know that we can use p series. P is equal to 1, which is less than or equal to 1, but greater than 0. Should move that. So the series diverges. Okay, So in the end, we know that the series, the harmonic series, 1 over n, diverges by p-series test. And therefore, the sum of from n equals 1 to infinity of 1 over 4 times the cube root of n minus 1 will also diverge by direct comparison tests. Okay, that's it. You know, another series, wow, wonder how long that's been there. And another series that you could use is to compare to instead of the harmonic series would have been 1. You could have also compared to 1 over n to the 1/3. It's a p-series. It's smaller than, at some point it's smaller than our original, and so that would be another one that you can compare to. Okay, that's it.